In this video, we will be analyzing electrical parameters of capacitors, specifically parallel plate. Now, a capacitor is an electrical component that stores energy between two conductive plates. Now, we will be analyzing the behavior and response of these in order to solve various configurations. Now, let's get started. For this problem, we are asked to determine the energy stored within a parallel plate capacitor with a potential difference of 50 volts, plate separation of 0.4 meters, and a plate area of 4 meters squared. Well, starting with a graphical representation, we can denote various parameters of the design, starting with our voltage across the two capacitors, V. Next, we can denote the separation as the distance between the two plates, d. Finally, we can utilize the area of the plates as A. Well, starting to solve for the energy stored, we utilize the following equation. Energy equals capacitance times voltage applied squared over 2. Now this is wonderful, but we yet know what our capacitance of this capacitor is. We know our voltage potential, but not the capacitance. In order to solve for this capacitance, we need to utilize a secondary equation. It is as follows. C equals epsilon A over D. Now, our epsilon is representative of the permittivity of free space. And this value has a constant aligned with air, which we will be utilizing for this example, of 8.85 times 10 to the negative 12th farads per meter. Now, utilizing this value and then substituting our variables known given in the problem, our area of 4 meters squared divided by our d, our distance or separation between the two plates of 0.4 meters. Solving for these, we can conclude that our capacitance of the capacitor is equal to 3.54 times 10 to the negative 11th farads. Therefore, we can take our capacitance straight into our energy equation. So copying over our capacitance and then plugging in the variables given as well in the problem, we have our voltage of 50 volts multiplied by the capacitance divided by 2. Therefore, finally, we are able to conclude that our energy is equal to 44.3 times 10 to the negative 9 joules, or simply 44 nanojoules. Thank you. For this problem, we have a 450 microfarad capacitor with a time-varying voltage source applied at its terminals. We will need to express the energy stored within the capacitor as a function of time. Well, we can once again use our energy equation equals capacitance multiplied by voltage potential squared divided by 2. We are given these values directly from the problem, so we can simply sub in our capacitance of 450 micro multiplied by our sinusoidal voltage 210 sine of 377 t. And this voltage is squared, and this is divided by 2. Plugging in and solving accordingly, we can determine that our voltage, this as a function of time, is equal to 9.92 sine squared 377 T joules. For this problem, we will calculate the charging current of a 300 microfarad capacitor when its voltage increases by 50 volts over a period of 6 seconds. In order to solve this, we will utilize the voltage function equation V of C as a function of time subtracted by the initial voltage of the capacitor is equal to 1 over the capacitance multiplied by the integral of 0 to t of the charging current as a function of tau d tau. Now, in order to solve this, we are not given specifically the voltage parameters, but we are given the increase or difference between the two gives us a voltage of 50. And this was equal to 1 over our capacitance, which is 300 microfarads. And evaluating this integral from 0 to t of the charging current gives us a product of the period multiplied by the charging current evaluated at that period. Therefore, plugging in to solve, we are able to conclude that our charging current of this capacitor is equal to 10.8 milliamps. For this problem, we are asked to calculate the equivalent capacitance of this circuit between terminals A and B. Well, simple reduction of these capacitors, we have a series connection as well as a parallel connection. Now, in creating equivalent elements of capacitors, we need to realize that it is opposite to how we approach resistors. Therefore, when two capacitors are in parallel, we simply add up their values, and then for series sets of capacitors, we will need to utilize reciprocal laws. So, starting with the simplest, we have our 4 microfarad and 4 microfarad capacitors. Therefore, simply creating an equivalent version, we can eliminate one of the capacitors and write in our new value of the summation of both, which will give us 8 microfarads. Therefore, we can see that we have a single series connection of 3 capacitive elements, 4 micro, 8 micro, and 8 micro. Therefore, using our reciprocal laws, we can find our equivalent capacitance, C, EQ, is equal to the reciprocal of 1 over 4 micro plus 1 over 8 micro plus 1 over 8 micro as well. Solving and simplifying, let's get this to a common denominator. Therefore, I can write this as 2 8 micro. Adding these values up, we get 1 over 2 plus 1 gives us 4 over 8 micro. Solving and simplifying, we are able to conclude that our capacitance of the equivalent circuit is equal to 8 over 4 micro, or simply 2 microfarads.